Okay, so let's begin. We'll start with the AZP, and as I said, so we'll begin using GeoDa for most of the applications. Only for the part of cluster validation, I'll show you quite pretty fast what GeoDa shows us as a result. But then it will be better to move to our Python notebook because then we'll have easier access to all the results for different methods. So it will be easier to compare them all. But we'll begin with GeoDa doing AZP. The cluster match map, we did it 2 weeks ago, right? So I think I'll skip that for today because we already have that recorded. But everything else we'll cover at least briefly so I can show you. Right, so to stick with the book, let's open the Ceará Zika file, the Ceará Zika data. Oops, here it is. And since today the focus is spatially constrained partitioning methods, let's begin straight with the AZP. So basically we'll use this small zone here of methods, right? AZP and MaxP, and then we'll see the validation part here in the clusters as well. Okay, so AZP. We'll keep using the same example as we did last week and following the book again. So we'll select these 5 different indices from Ceará. So mobility, environment, housing, sanitation, and infrastructure. And in addition to these 5 indices, we'll also use the GDP per capita. So we just need to go a bit below in the list. And here it is. Right, so it's the same 6 variables we used last week. And then, of course, it's very important when we're comparing results, we want to use the same variables. So this is the reason why we're sticking to the same. Another thing, since it's spatially constrained clusters, we do need to select a spatial weights. If you still have the one from last week saved, you can just load it. I'll just create a new one again. So I'll come to create, and then choose an ID variable, the code for the municipalities in Ceará, and then contiguity. So let's just do a simple first order queen contiguity matrix. Create. I'll save it in my desktop. Just do a Q1, so no, it's a queen first order. And that's it. So now we can close all these weight file creation window and everything related to the weights because we checked it already and we know it works fine. All right, so now we have the basics set up. So we have the variables, we have our weights matrix. So now we can check the parameters and see what we want to do. Of course, as we did for the other methods, we'll begin with the default values for these parameters, but it's already good if we can just check them all and see exactly what they do. So for number of regions, since we're working with a partitioning method, that is a requirement, right? So we do need to inform first how many regions we want because the optimization will be based on that number of regions. For the max speed, it will be different because the requirement will not be the number of regions, but actually the minimum size of the regions, right? That's where how the optimization will be based. But here for the AZP, we do need to provide the number of regions. And in last week, we talked a lot about 12. That was what we used for the spatially constrained hierarchical clusters and for the scalar, I think. Anyway, so to follow the book again, let's do 12. For method, we'll use the default AZP. The result will not be good because, as Luke mentioned, one issue with the AZP is that given that the way it works is that it will select random regions in our map and then just assign the neighbors, it's very easy to follow into a local trap, right? So the AZP will likely not yield good results, but then we'll come back here and we'll check the taboo search and then also the simulated annealing. But let's begin with the standard AZP. So since it's a standard AZP, these parameters are not available for us to work with. Minimum region size, we worked with this already, like in other methods, so we know how this works. So there's no need to talk about this, but yeah, it's just the idea that we would require, once thinking about the method, we would require at least a minimum number of regions should be part of the cluster for it to be feasible. Distance function, we'll use Euclidean. Transformation, again, we need to standardize our variables because they come in different unit measures. Okay, all good? Right, so one thing that is important, especially since we will work with some validation afterwards, is that we pay attention to the columns that we're creating, right? So the cluster labels that we are, for the clusters that we're creating, so the assignments for each unit to their clusters. So here, I'll make sure to change the name here to CL AZP, just so we have it stored and we can identify what we did. Okay, so run. Right, so this is what we get in terms of a map. So we can see that there is one singleton, so it's not too bad. Actually, this singleton is quite kind of a singleton, like for real, because it's the capital of the state of Ceará, Fortaleza. So it does have very different attributes. So the presence of the singleton is not a big issue. However, in addition to the singleton, we have 3 other regions that have like less than 5 observations, 5 spatial units in these clusters, right? So this may not be good. We have like many regions that are very small. So the overall balance does not look very nice, right? We have some regions that have quite similar number of observations in them, in some of these clusters, but for the others, we have very few observations. So anyway, it's one thing to keep in mind when evaluating these clusters. What we have here in the summary of the results is, again, as for most of the methods, we get the cluster centers. So here we have the average of the mobility index for cluster 1, the average environment, the index of environmental, I forgot what else, the environment index for cluster 1, and then there you go. Right, so this is what we would use to be able to label the clusters. So here, for example, for cluster 12, the city of Fortaleza, we know that it's a cluster of like very high GDP per capita, the low, but not that different, but low infrastructure. Again, average sanitation, housing is a bit too low. Environment is also lower than the average, and there you go, right? And especially mobility is very low. I think it's the lowest value. No, there's just one lower than it. Okay, so this would help us to, again, label these clusters. Let's just not worry with labeling it yet, because we need to make sure that we have a result that we're happy with. And if we check this, so the balance for the number of observations is not that good. The balance for the within cluster sum of square, again, not that good. We have some clusters that are very homogeneous, others are not. And most importantly, if we check the ratio of between to total sum of squares, it's only of 0.37, right? So not good at all. We have a lot of heterogeneity within the clusters and not that many between the clusters. So this is not what we actually want. So it may be that we're falling into a local optimum trap when we're running this. So now we can change the method and see if it will help us go beyond this local trap and find a better global optimum. So let's just do taboo search first. And when we change the method to taboo search, we can finally tweak with the taboo length and the conv taboo parameters. So the taboo length is just the length of the, like for how many iterations you will keep the forbidden moves stored, right? So it's the idea that, for example, once you change a region to another cluster, that will become a forbidden movement for the following iterations, right? Because you don't want to cycle back and forward all the time the regions when you're running the optimizations. So taboo length will control that. So how long these movements will be banned in that sense, right? They will become forbidden movements during the optimization. And the conv taboo, what this will set is it will control kind of the allowance that you will have in the method for iterations or for changes that will not improve the optimization, right? So this is where the whole idea of going out of the local optimum trap occurs, right? Because once you're in a local optimum trap, you'll be always doing movements that will be improving your goal, right? Improving the objective that you have in your function, the optimization function. But then again, you're locked into this local optimum. So you may want to do one movement that does not improve the optimization, does not improve, sorry, the objective function, but then it may move you to a different area in the whole optimization procedure. Does it make sense? So this convo taboo is exactly that. It allows us to like control how many times we want the optimization procedure to run these iterations or these steps that are not improving the objective function. Okay, so its default value, if we leave it blank, it will have an internal formula to compute the default value. I don't really remember what that formula is, but it's in the book. So let's just leave it as it is. And then we can compare the result that we get from this default taboo search and the AZP, like the classic AZP. All good? So I'll hit, oops, I'll change the name here to taboo and then hit run. So if we compare the maps, I mean, at first they pretty much look identical, right? There isn't much difference. We know that the result is different because the number of observations, the number of spatial units in each cluster did change, but the changes were very minor. So we can't tell much difference between these two solutions. If we see the summary, we can go straight to the ratio of between two total sum of squares. And you'll see that with this, the default values for taboo search, so the conv taboo was computed as 15, using this internal formula. So what we get is a 0.37 BSS to TSS. If we compare to what we had before, it's basically the same, right? 0.37, but 37 to 3. And now it's 0.37, but 37 to 4. I mean, it's just the fourth decimal gain, right? So it was not good. So maybe this convo, like the amount of non-improving steps that we took, and also the length of the taboo length that we have, so the length of the forbidden movements, maybe did not help as much to avoid any local optimum, right? So we can change these. And in the example like that Luke uses in his book, the taboo length is of 50 and conv tab is 25. So we may ask, like, where did these values come from? From experimentation, right? So you do have to keep working on them and increasing them and seeing if you get different values or not. Because if what you had was already a global optimum, then even though you increase a lot the conv taboo or any of these parameters, you shouldn't get a very different solution, right? But you may. The method may be very sensitive to what you set here. So anyway, it is a matter of experimentation. So you should play with different numbers to see what you get. So here with 50 and 25, we know we get some improvement. I won't even change the name. Let's just override it. Sorry. So yeah. And here's the new solution that we get. Let me close this one, and then we can compare again. So this is our original AZP solution. This is our new taboo search solution. So again, if we look at the map, very similar still. So the difference is basically in these regions. As Luke said, a good way in GeoDa to compare the results is just to click in any of our clusters. So for example, in our taboo search result, if we click in this rose colored cluster here, you can see that all units that are part of this rose-colored cluster, the 14 units that make up this cluster, they are all in this cluster 3 in the original AZP, right? So they were all in the same cluster before, but this cluster before, cluster 3, was much larger. And it also comprised units that are now, in cluster 6 and cluster 1. Okay, so we can see exactly how the solution, the new solution was, where the new solution improved the previous result. And another part that changed a lot is the southern area in Ceará. So this new cluster 3, again, most of the units that were previously part of cluster 5 in the AZP, they are still clustered together. I think there are only 2 or 3 of them that are not. But in the new solution, we get a lot of spatial units that were previously on cluster 1, and they are now part of this new cluster 3. Okay, so since all the results are linked, by clicking on any of the clusters, you can visualize exactly what were the changes. Let's see what we got in terms of improvement in the ratio of between two total sum of squares. So yeah, so now we did get something more meaningful, like at least the second digit. So from 37, it increased to 40. All good? Yep. So, I mean, it improved, but it's still very worse than what we had before with the other methods that we saw last week. So if we want to use any of these partitioning methods, we may need to play more with the parameters and try to find, or the methods, the optimization methods, to try to find something that is more comparable and more in line with what we had before. So another step to do that is still doing AZP, is to try the simulated annealing. So with simulated annealing, now we have a cooling rate and a maximum number of iterations, right? So the whole idea of the cooling rate is, again, to control how many movements that will do that will not improve the optimum. But then these numbers will decrease, like the allowance that we have for these non-improving movements will decrease over the movements that we do. So that is the whole idea of the cooling rate, right? So as farther as you go in the optimization, we will allow less movements that will not improve the optimum. Does it make sense? Right? So
why is it not the other way?
What do you mean?
The lowest hanging fruit is at the beginning, and as we move towards the top or the bottom, we look at it, it would seem that then would be the non-improving moves would be more helpful.
But then, if you think about how the method is working, the biggest issue is the initial solution, right, where you start. And then you're just playing with reallocation. So that's why at the beginning you should allow for, you should allow for like different changes, more radical changes in that sense, because it's where it's more critical. Once you step more and more and more into the, like, by the endings of the optimization procedure, you're just kind of making very minor adjustments and changing one region to the other and to the other cluster. So then you can just be more strict to do less possibilities, and computationally it will be better, right? Luke, if you want to pitch in to help me with these questions, please.
No, this is exactly what the purpose is. So if you remember the inequality, that's really the key to it all. And this is a very general principle. It comes back in MCMC and in different Bayesian decision sampling decisions. So you basically create a random improvement where the chance of the improvement decreases, a, a random non-improvement, I should say, where the chance of the non-improvement decreases as you get further into an optimization process. So if you look at the inequality, let me get this right. On the left-hand side is a uniform random number. So the mean of that is 0.5, right? And so if you just assume you get 0.5 each time, if on the right-hand side, you start at 0.8 and then it goes to 0.7, 0.6, 0.5, 0.4, now the chances that you actually make a non-improvement move are less than 50-50. Of course, it's a little more complicated than that because in addition, so there's two things working here. One is this probability thing. The other one is that you say, I don't want to do more than X number of non-improvement moves, right? The default is 1, which doesn't make a lot of sense, but you know, if you say no more than 5, definitely not 100, right? So, but those numbers, there's really no guidance to set them. And the only way that I've found is to get a better sense for them is to trial and error, you know? I mean, not really error, just try. Try different combinations and see how it works out. And that's how I ended up with this number that gave at least a better solution than the default settings. But it's very sensitive and it depends on the data and all this kind of stuff. On the weights, also not to forget, you know. So that's where the researchers' degrees of freedom come into play, right? You can, I mean, this can be manipulated. I mean, if you have an audience that has no idea what you're talking about, you can present your favorite solution, even though that may not be the best solution in terms of a given set of criteria. Right? And that's also why we look at multiple criteria of validation. You know, what is good, like the the one that we have in AZP tends to do this, and since max P is basically AZP, after you find an initial solution, you tend to end up with these stringy solutions, which you can see in the map. There's a couple of examples where they're totally not compact. And for some, you know, problems like surface areas, that's not a good solution, right? You know, surface area, you don't want to drive too far. And so then the compactness comes into play. And we don't have that yet, but that's another recent addition to the menu of the spatially constrained methods.
Yeah. Okay, so shall we see what we get from these? So let's hit run. Again, I mean, just before I hit run, let's get the intuition of what we're doing. So basically, we're allowing only one iteration, and we have this cooling rate that is 0.85, meaning that, again, the speed at which the unimprovement moves will be allowed, so that the speed of which will decrease the allowance that you have for unimproving movements will not be like too slow, or I mean, it will. You see, we could do 90, that's what we'll do. Afterwards, 95, which basically will be saying that we will make it slower, right? So we will increase our allowance for non-improvement movements. So by doing 85 and 1, we may not change that. The 1, of course, is not really helpful to avoid local optimum. The 85 is better, but it could be even more. Like the greater number would increase the allowance for these unimprovement movements. Sorry? Thank you. I would totally have forgotten. So here, let's just do SA, right? So hit run. Okay, this is the result that we got. And compare it against what we had from the taboo. So now we are starting to see more changes, right? So if we see what we got from these the SA solution and compare to the taboo solution, then the simulated annealing does show more differences. Before we go into more details, let's see what we got here for the results. So with this cooling rate and maximum iteration number, we got a ratio of between two total sum of squares of 41, 46. So it is some improvement, but again, we can try to do better. And to do better, maybe we can allow for more unimproving movements. And by doing so, we could, for example, increase this to 0.90. And actually, in the book, Luke does here 0.8, and the maximum iterations is where he increases it to 5, right? So you do more iterations within each of the steps. Okay. So let's run again. So in the solution with 0.8 and a maximum iterations of 5, now the ratio of between two total sum of squares increased more to 0.4368. So like we're in each of these steps that we are taking, we are being able to decrease the internal heterogeneity in our clusters and increase the between heterogeneity, right? So how different the clusters are from each other, which is good. But again, do keep in mind that although we're looking at these statistics most of the time, it's not the only thing that matters, right? Because it's not only about making sure that the clusters are internally homogeneous and between themselves they are very different, because if that is what we want, the k-means would be probably the best solution for us. So that's why in the validation procedure, we'll check different statistics or different measurements for our clusters, because we're not really worried only with homogeneity, right? The thing that we're doing here, the reason why I'm looking a lot to this value is that we are already departing from the constraint of spatial contiguity, right? So this is a constraint we already added to our solution because it is important. So when I look at these two solutions, and if you look at them, you may notice that the whole idea of compactness of the clusters is not really good, right? So check the format of these clusters here. So if we are thinking about this, the spatial structure of the cluster, if the spatial structure is really something that is very important to us in the sense that the cluster is very concise, right? So it's the shape of the cluster is something that is very, well behaved in that sense, maybe this result was not good. So again, it's all about a trade-off, right? So the more
Pedro,
yes,
another point is that these outcomes are sensitive to some potentially weird things in the spatial weights. And in fact, I have noticed this in the Sierra example. There are some artifacts of the digitization that result in corner solutions. So you get these weird things like on the AZP essay, cluster 5, and cluster 1. There seems to be a, a contradiction between 5 seems to be cut off by 1, but it's actually, when you look at the weights, it's not true. And so this is an artifact of the digitization that it's very weird. See, it's the little corner solution. See the edge? It turns out it's the worst possible
disagreement.
case. See? And so these kinds of things throw you for a loop. And you look at the result, you say that doesn't make any sense. But then what you should do is actually edit the weights if you deem this to be inappropriate. Sometimes it doesn't matter, but they actually do touch, but it's very bizarre.
So it's good that we're talking about this now, because then we can already start trying to identify the validation measures that we'll use. So for example, if we look at the result that we have here for cluster 7, and we think about its compactness, basically, if you compare the shape of this cluster to a circle, it's quite similar, right? So it will be a cluster that will score high in compactness. And also, if you see how close the spatial units are from each other in terms of how many moves you have to do from one element to the one that is farthest from it within the weights matrix, you can tell that the diameter is also small, right? So it's kind of a well-shaped cluster in terms of its spatial structure. Whether if we look at cluster 5, as Luke was mentioning, and we think about it in terms of compactness, maybe it will not be too bad because still, right, a circle, it's not too far from its shape. But in terms of diameter, it will be really bad because the number of moves that we need to take to go from this unit to, I would say, maybe this or the other one. I don't know. Any of these would be the farthest neighbor. So the number of moves that we need to take is just a lot in comparison to how many neighbors we have within this cluster, right? So this is the whole idea of the validation measures that we'll see in the end of the lab today, like the final, especially in the notebook, but also GeoDa will show us these things as well. So it's the whole idea of trying to help you when you're deciding what method you'll stick with, what will be like your method of choice, to help you balance these things in your trade-off, right? So the whole idea of spatial structure, contiguity is given because it's a constrained method, but maybe contiguity is not enough, right? It really depends that maybe the shape is important to your objective as well. So these will be the measures that we will use. And since I'm already talking about them and I've opened this parenthesis, of course, I'll kind of go back to this later. But the other thing that we will look at will be the join count. And what the join count will do is basically count what we have. So let's look at this cluster 11. We have only 2 units, right? So when we look at it, we will see how many neighbors each of these 2 units have. Of course, they are neighbors of each other, again, spatially constrained, right? So we'll always have that units in the cluster will have some connection between them. These 2, since are only 2, they will be connected. So the join count will count how many neighbors they have between themselves and how many of their neighbors belong to different clusters, okay? So in this case, I mean, it's only 2. It's not really much help, a lot of help. But for the dark green here, so it will count, okay, so this unit, it has all those neighbors. Of these neighbors, there are 3 of them or 4 of them that are part of the same cluster that unit is. The other ones are blue, so they are not part of the same cluster. Then we'll have the join count ratio that will tell us this proportion. Okay? And finally, since I'm talking about them all, we have the fragmentation or the balance measures that will pretty much look at how many spatial units we have in each of them and see what is the heterogeneity that we have here, right? So the entropy and the Simpson's index will just check like what is the imbalance that we have in the number of units that we have in each of the clusters. Okay, so once we go to the validation measures, we'll talk about these again, but start for all the solutions that we find, already try to identify these measures and think about the cluster solution, considering them in the end. Okay, so let's keep moving with our AZP and all the options that we have. So the next one is the RSL. So the RSL, as Luke mentioned in the first part of the lecture today, it will kind of work as the k-means plus, and so sort of redo the method with, different solutions, right? Different initial solutions. So if we check here, it will just do 10 construction reruns, right? So it will see whether by changing these inits, we get to a better optimum. So, I mean, I'll run it again. I'll run it now. Resell and run. So this is the result that we get. So now the ratio between increased slightly more. Now we are at 44 out of the 43.6, now 44.2. So we keep increasing it. We just need to assess again whether the solution that we have for our clusters does make more sense or less, and what we think about this. So I won't spend much time here. I'll just keep moving because we still have many things to see. Minimum region size, I won't do it. Let's just skip because we talked about this already. What is important here that is really interesting in AZP is the possibility of, instead of just running different initial solutions, like random different initial solutions, what we can do is choose the initial solution ourselves, right? So for this, one approach that usually provides good results is if we do a hierarchical approach first to see what we get. But then, as Luke said again, remember that in the hierarchical approach, you are always bound to the decisions that were taken in the previous steps, right, in the dendrogram. So if you're thinking about a hierarchical approach that is agglomerative, units that were merged will forever be merged until you merge all the units in your sample. If you have a divisive approach, units that were split will forever be split again, right, until you reach the final solution where each unit belongs to its own cluster. So if we use that hierarchical initial solution and we apply here in the AZP, basically what we'll be doing is considering that number of clusters and that cluster location, we'll be seeing whether it's possible to do some local moves and maybe some reassignments of the units that the dendrogram would not allow us to do because how rigid the hierarchical step-by-step procedure is. We'll be just reassessing this and seeing whether it's possible to find something like some ways to improve the solution by doing some local movements. Of course, to use something like a result from a different method, to use it as initial solution here, we need to have that method solution, right? So first, since we started over from last week, let's go back to clusters. And let's run the spatially constrained hierarchical clustering again. So here I'll choose the 6 variables again. So all the indices plus GDP per capita. Number of clusters, 12. So same spatial weights, standardized, wards, everything's the same. Just here we need to make sure that we give the correct name. So spatially constrained hierarchical clustering. Run, and then save. I won't check the map. I mean, we talked about it last week, so I'll just close everything. I just wanted the labels. And now that we have the labels, all good? Do you need to wait? No, no need for waiting. Okay. So now that we have the labels, we can just check the box here for initial regions and find the labels that we just created. So here, CLSCHC. Change the name for AZP SCHC. And then what we'll have is that, oh, sorry. I'll change here to simulated annealing again. And yeah, let's keep the same cooling rate and maximum iterations. And hit run. Okay, so now we have more singletons, right? We have 3 units that are singletons in our result. And if we check the ratio of between two total sum of squares, it increased even more. So now we are in the 50s already. So finally, we have crossed the threshold where we have more heterogeneity between the clusters than we have within the clusters, right? So that is a good thing. But then the spatial structure of our clusters is the balance is worse because now we have more singletons. But the shape of the clusters is, I mean, some are bad like this, but others are still concise or compact. So again, it's really, as Luke said, it's all about the researcher here, like what you need and what fits better your objective and the objective of your research. Is it okay? Yep. So for between all these AZP solutions, again, what we saw is that there is a trade-off between spatial structure again and the ratio of like the homogeneity that you have within the clusters. So you have to balance these things out. However, this last solution, even though it is less balanced, the number of units, it did show a much improved internal homogeneity in the clusters. So my personal view of this is that from all the AZP solutions that we tested, I would likely stick with this one unless the shape of the clusters was something, or at least the minimum number of regions and all of that was something that was really important to me. And if that was the case, you can still play with the parameters, you can still add minimum number of regions and all of that to make sure you get an even better result, right? Any questions about the AZP? No? So let's move forward to, oh no, yeah, let's move forward to the MaxP. Close this, I may want to go back to it. I'll just close this window. And clusters again, MaxP. So MaxP is different, even though it will use, like it will be based on the AZP. It's kind of AZP with a pre-analysis first, right? So the whole idea is to try to find a better initial solution in terms of what you need. But more than that, in the MaxP, it's not only a matter of finding or trying to find a better initial solution for the AZP, but a matter of trying, like not having to decide a priori how many clusters you have in your data. So this is the biggest advantage of MaxP, because it's the only of these methods, of these partitioning methods, that we do not have to set the number of regions first, right? We can set the minimum region size, so there is still, it's not that we're like free from deciding, right? So the researcher is still very important and it will impact the result that we get. It's just that we don't need to decide on the number of clusters. Maybe we have some other orientation about like how many regions we need in each of our clusters, or how many, like what share of the population, that's the example that we will use, share of population or any variable that we have, like we need a minimum amount of that variable. Maybe it's about, I don't know, passengers for a public transportation system, or, you know, bus stops, or a number of crimes or stores or whatever. As long as we have something that we know we need a minimum of that in each of the clusters, then we're good to go. So this is the idea. In MaxP then, we need to set either the minimum region size or the minimum bound, because based on this, the MaxP will run its optimization. So let's select here the 5 variables of the indices, and then the 6th, the GDP per capita. And let's begin with the minimum bound for population. So I'll find pop here. And the default here is 10%. So let's keep it. So in this solution, what MaxP will do is it will randomly draw some of our regions, right? And then see, like, is this spatial unit, like, how far is it from the minimum bound? And then it will start merging the neighbors of those units, and again, assessing how the variables sum over them all, right? So with 2 solutions, how much population I have, with 2 units, with 3 units, then you'll start merging the neighbors until you reach the threshold. Once you reach the threshold, you're good, and then the method will jump to another random draw and will start over, right? Trying to form a second region. And it will do that all the way until it can reach as many regions as possible. That is the idea. That's the MaxP. It will try to maximize the number of regions it can create based only in the minimum bound. Okay, so it will not be looking at first at anything else, just the minimum bound, to make sure it can create as much regions as possible. Once it reaches this maximum number of regions, not all spatial units will be assigned to the regions, right? Some of them, as Luke showed, will be out of any of these regions. Then it will assess with all the variables that we have selected, where those regions that are unassigned, where should they go? The enclaves, right? So where should they go? And then based on the optimization that you're doing, basically it will check the within sum of squares to see where the units that were still not assigned, where they should go. So again, you can see that the MaxP method is again very sensitive to these random draws, the initial solutions that it gets, right? Because the first regionalization will be solely based on that, on the random draws and meeting the minimum bounds. That's why the number of iterations is a very important parameter that we have in the MaxP. 99 is usually not enough, so we will increase this. Let's just run with the defaults first, but then we'll change this. And we can start with the greedy local search. So it will try to do like it will be greeting the changes that it's doing between the different iterations, right? To try to find better solutions. But then since it's basically the standard AZP, but then we can also use the taboo search and the simulated annealing to try to get better optimization after this initial regionalization based on the minimum bound was done. Is the intuition clear for everyone? Like what is the difference between MaxP and AZP? So the difference is that how MaxP first begins the regionalization based on the minimum bound, trying to get as many regions as possible, and then it will do the AZP afterwards. All right, so everything set to default. I'll just change the name to MaxP and run. So finally, we get something that is very different, right? Since we said that the minimum bound is 10% of the population, with 10% of the population, the maximum number of regions that the method could find was 6. So half of what we were doing before, right? So maybe if we want more regions, maybe we just set a bound that was too high and we need to decrease it so MaxP can increase the number of regions. So the more we decrease the bound, of course, more regions MaxP will be able to find and then run the optimization based on that number. So I'll close this solution. And let's move the population, let's say cut it by half and do 5%. And then we can hit run again. And now here we have 12. Okay, so now we have 12 solutions. So this 12 regions, sorry, 12 regions in this solution. So this again was the maximum that MaxP could find. And you can see that the balance that we have is much better. So we have a smaller fragmentation in terms of the cluster allocations. So we don't have any singletons. The minimum region size is 4, and then everything else is distributed around this because, of course, we set a minimum bound. Right? So that's what we set from the parameters. So that's what we should find anyway. However, we can still be locked into a local optimum here. So I'll close this solution. I'll increase the number of iterations. And then, I mean, just so it's not very repetitive, I'll skip taboo search and go straight to simulated annealing because it showed us the best result, right, when we were doing the AZP. So I'll go straight to this. And we can set a cooling rate, let's say, of 0.9 with the 5 maximum iterations. Again, the distance function Euclidean. We will standardize the variables, of course. I'll not change this. I'll just replace the result that we had before and keep this as MaxP and run. Now I've hit run already and I'm still waiting. So I don't know about you, but see, this is not going anywhere. Not sure if you could see that like the running sign was shown very briefly, but it was shown here. My cursor became that running sign because now we have almost 10,000 iterations. right? So with 10,000 iterations, it takes longer to do all these simulations. So that's why, as Luke said, depending on your sample size, so how many observations you have, maybe MaxP will not be a good approach if you have too many observations, because you will have to run very few iterations, so the risk of falling into a local optimum trap will be very high. Okay, let's see what we got for a solution. So you see that the summary is exactly the same that we had for the AZP, because you were just changing this previous step. And what we have now with this cooling rate of 0.9 and maximum iteration of 5 is a ratio of between two total sum of squares of 0.38. Okay, so it's smaller than what we had before, but again, in the trade-off, now we have a more balanced solution or a less fragmented solution, right? Because we have this minimum bound, so we know that all of our clusters meet the 5% population criterion. Whereas in the solution before, we do not know. Since now the object, it's not the objective function, but the homogeneity index is worse, likely that 5% was not being met in our previous solution. Does it make sense? Yep.
Yeah, Pedro, it's also good to reiterate that anytime you impose a constraint of any sort, the result will be worse than an unconstrained counterpart. So the other AZP with a P equal to 12 is unconstrained. The clusters can be as small as they want, and we have some singletons. Now here we're saying, no, no more, you have to have at least this number of population. And so we'll never be able to do as well as that unconstrained solution. But what you get in return is that you get, as it turns out, 12 as the maximum of P. So if we had, say, run the standard AZP with P equals 6, we could be doing better with max speed than the unconstrained with P equals 6. But we'll never be able to do better than the unconstrained with the same P because we impose a constraint. It's like, when you look at the R square in a regression. Anytime you add a new variable, you have a higher R square because the constrained model is the model with that variable removed is worse, and so has a smaller R square. It's the same thing. But we have multiple balls in the air here, so we let the constraint, the size of the cluster, be the driver of this algorithm. If that is not a concern, then we should never do a constrained optimization when we can do an unconstrained one, right? So it's kind of nice if you say, okay, I have to report a rate for this very rare cancer, and because of privacy considerations, we have to have at least 250,000 people in whatever our reporting unit is. What is the greatest spatial detail we can get? In other words, what is the highest P we can get to report these rates in meaningful units that are spatially connected? So that is the kind of application where max P makes a lot of sense. The type of results that one gets tend to be more stringy than one would like. So they tend to be not very compact regions.
Yeah, so as we can see here, what was the expression? Look, that it's snaky, right? But something like
Yeah,
this.
snaky. Yeah.
Yeah.
Snaky and stringy.
So
And then we have these little artifacts, of course, due to the weights matrix, where we see them seemingly jump over another cluster, but they're actually not.
Yeah, if this is something that really you don't want in your result, maybe you could just change the weights matrix that you're using, right? Instead of doing queen, you could do k and k nearest neighbors, and then this would not happen. Because then,
Well, actually, the problem with k-nearest neighbors is depending on the density or equivalently on the relative sizes of the areas, you can get very strange results too. If you recall the Italian banks, some of the k-nearest neighbors would cross the Mediterranean and go to Sardinia. And so then, that also is not necessarily ideal. But it gets back to our basic point, don't take these weights just at first sight. You have to think about them. And if you see things in the solution that are strange because of your weights, then by all means rethink the weights. There's nothing magic about Queen's contiguity. It has to make sense.
yeah. In this case of Ceará, that is very compact, then the KNN would likely yield more concise results, right? Because in the Italy banks, as you said, you have actual islands that the KNN is able to jump them. So yeah. And one expression that Luke just said that it's really important to think about in the MaxP is that here we have many balls in the air, right? And maybe it may be too many because we have too many parameters that we're setting for this MaxP. And therefore, the solution for the method, it's sensitive to too many decisions, too many choices, right? So this is something that we need to think about when using any of these methods. I think what Luke says in the book is that at first this may be a bit discomforting in the sense that we have a lot of subjectiveness in these solutions, right? So that's why, again, we started saying that cluster analysis is kind of an art, because it is. There is a lot of input from the researcher in the solution that you'll get here. But it's the whole idea that you are able to shape the results or to find the best result that you can for the objective of your research, not just the objective function. So there is this whole unsupervised idea in these optimizations, right? In these machine learning methods that we're using. And but the researcher input here is really important. And that is part of the whole idea of clustering analysis, that why you're running this and your prior knowledge to the variables that you're using, the region that you're working with, it's really important for you to be able to choose exactly what will be the best solution. Because the best solution quantitatively may not be exactly the same thing as what you need in terms of what the whole research is about, right? Because again, there are all these things that you're balancing out and try to find the optimum balance between them all. Okay, so we're done with all the methods. Can we move forward to validation? All right. So as I said, I already did the cluster match map. I won't do it again because basically what it will do, as Luke said, it is just like this. For example, we'll choose here in the MaxP solution, maybe we could choose cluster 1 and then compare it against the AZP taboo search that we had before. So the cluster match map would just show us exactly how many of the 29 observations that we have in the MaxP solution, how are they distributed in the taboo search solution, right? So it will show us that out of the 29, we have one that is rose, we have one that is brown, we have 4 or 5 that are light blue, and there you go, right? So it would just highlight these changes and make them automatic for you. So it would count the regions and tell you exactly how they are distributed. So again, if you want to review that, go back 2 weeks in our lab and it will be there. Now let's just go to validation. I'll do this pretty fast because then we'll go to our notebook and there we'll have a much broader view of this. But the whole idea of the validation measures that we have is that they will show all these things we've been talking about for any given result that we have. So for example, if we see the CL AZP SCHC solution, I'll hit OK here. it will show us the entropy that we have in this solution, right? So if we look at the standardized entropy or the standardized Simpson, what we have here is that it's basically assessing the balance that we have in the number of units that we have in each cluster. And if they all had this exact same number of units, the entropy would be 1. So it would show like that we have a better, like a great balance, right? So as close to 1 we have, the better the balance that we have in the entropy. And for the Simpson, it's basically the idea of diversity. So the greater the value that we have, the more diversity we have in the number of units that we have in each of our clusters. So again, we want it to be also for more balanced regions, so less fragmentation. We want it to be closer to 1 as well, because that would be show us that we have less fragmentation. The joint count is showing us, as I said, just counting. So for example, here is the solution, right? So here in cluster 1, we have 95 observations. So when we consider all the 95 observations together, they have 505 neighbors. And what the joint count is doing is counting how many of these neighbors, so of the links that we have within or across all the units in this cluster, how many of these 505, how many are part of the same cluster, right? So of all the 505 links that we have, or edges that we have in our weights graph, 368 connect units that are part of this very same cluster. Right? So this is the idea. So the ratio is 73%. So it's a high ratio, showing that the spatial conciseness of this cluster, or the spatial, I don't know, the similarity, the spatial similarity that we have in this cluster is very high. For this, let's say a smaller cluster will be easier here. They're all large. Anyway, so for cluster 2, again, we have 50%. So if we highlight that solution, where was it? I moved the map and now I lost it. This is it. So for cluster 2, it has 39 units, and then half of the links are within the cluster, so part of the same cluster, half are with spatial units that are out of that cluster, right? So again, it shows how not very spatially similar these units are, right? So the neighbors of the units that belong to this cluster are not, many of them are not part of the same cluster. So the conciseness, the spatial conciseness is not very good. Okay. Next thing, compactness. So I talked about it already. Compactness is pretty much drawing a circle around the cluster and seeing how much of the area of the circle is made of the cluster itself. So the greater to 1, it means that it's better, right? The cluster is more compact. The farther you are, like the closer to 0, it means that it's not compact at all. For these measures, it's interesting if you note what we get for the singletons. Because if you think about it in the other, like the homogeneity that we have in the singleton is maximum, right? There's no heterogeneity, it's only one unit. But since the units may have very odd shapes, something that is very non-circular, even if you have only one unit, you may have compactness measures that will be small. So for example, cluster 12. Cluster 12, I think, was Fortaleza only, right? I think it's just the capital. Yeah, no. It's this large city here. Anyway, for this city, it's just one unit, one municipality. But its compactness is very small. It's 0.35, right? Because again, it's based on the shape of the polygon. So you're seeing the shape of the polygon of the cluster and comparing that polygon to a circle. If you have only one unit, that will be the polygon that will be compared to the circle. The diameter, it's different.
Pedro, if you compare that to number 10, you can really see the contrast.
Okay, let me see what is number 10.
It's also a singleton.
Oh, it's much more circular, right?
Yeah, right.
So that's why the compactness is much higher. It's 54. because if you draw a circle around it, 54% of the area of the circle will be in the polygon, right? Will be comprised of the polygon, right? So now diameter, if we
You
see,
see, in this one, the IPQ has been corrected. In the slide that I showed you, it said IPC.
you see that is true. So you are the one with the older versions of GeoDa now.
Yeah.
So yeah, this is correctly spelled. So for diameter, what it's doing is, again, seeing this spatial conciseness of the cluster, but looking at it from the perspective of the weights matrix. So the graph that we have in the weights matrix. So if we look, for example, at this cluster 6, basically it is checking how many moves I need to do to go from this unit to that one. Okay, because they are the farthest one. So like the order of neighborhood is, this is a first order neighbor of the first unit. This is a second order. This is a third order. So I did three moves to get to the latest one, right? So this is how the diameter will be calculated. Whereas if I check the purple one here, I do only one move to go from the beginning to the end of the cluster, those that are farthest from each other. So this is what will be measured here. So for example, as I said, for cluster 6, the red one, you have the number of steps as 3, right? So the value, the ratio is 75 because you had 4 steps and you needed 3 to reach them all. You have 4 members in the cluster and you needed n-1. Basically, you needed all the steps possible to reach the final one. So for the singletons, the diameter will be 0, right? Because you don't have to do any move and you have already the whole cluster. So it's not a meaningful measure for singletons. And it's a measure that really depends on also how many units you have in the cluster, right? Because then, of course, you tend to have a greater, tend to need more steps if you have more units. So that's why you divide the number of steps to what you have in terms of number of units in the cluster. Okay, shall we be done with GeoDa and move pretty fast to the notebook? Right, let me close everything here. No, I don't want to save my data. Let me open the notebook. I won't run it live, so just trust me, I did it already. Luke did it as well, so at least if all the configuration is correct, it will work. One thing that you need, or things that you need to make this notebook work, is you need to import pretty much all the clustering functions that we use from sklearn, from scikit-learn, because here in this notebook, we want to compare them all, right? So we start from k-means, which we saw, I don't know how many weeks ago. We'll use hierarchical clustering. For do that, we need to do the scalar. So we standardize our data, and then some usual metrics. So they're adjusted rand, and there you go. And also you need to use our supplementary, our helper file with the helper functions that we added for the notebooks. So it's required because pretty much everything we'll do for the validation will come from there. For the methods that come from PyGeoda, so the AZP, MaxP, spatially constrained hierarchical clusters, scatter, then PyGeoda will already contain several of the information that we'll use, so it will be simpler. But for hierarchical clustering and k-means, then we'll really need everything else from the helper functions. Okay, so I'll just move forward here and go to what really matters. So what we're doing here at the first part of this notebook is basically running all the clustering methods to store the results, right? So we'll have all the information. So here we're running hierarchical clustering, and it's showing us exactly what is the cardinality, so how many units we have in each of our clusters. K-means, SCHC, scatter, redcap, AZP, AZP with the SCHC as initial solution, and finally MaxP regions, right? So these are the methods that we will compare. You can see that again, for all those that come from GeoDa, it's quite simple. We're just running PyGeoda and then saving the results, saving the labels. But for the others, like k-means and especially hierarchical clustering, we need to work a bit more to make sure that the results come out in a way that we expect them and with all the information. One important thing to say is that MaxP regions results in a different number of clusters when we're running it on Python in comparison to what we had in GeoDa, as Luke mentioned before. So that's why for all the other methods here, we're using 13 regions instead of 12, because MaxP will result in 13 with these parameters, right? So we're still using almost 10,000 iterations. The cooling rate is of 0.9, and the number of iterations in the AZP is 5, right? So, and the minimum bounds here is 5% of the population. So it's basically what we did in GeoDa, we're doing here, but in GeoDa we had 12 as the MaxP, and in Python we get a slightly better result. We get 13 in that sense. Okay, so that's why all the other methods are also set for 13 regions, so we can get the exact same number of regions, then it's easier to compare, or it's actually feasible to compare these validation measures that we have. All right, so as I said, here we're checking, like creating the internal validation measures. We're creating it for the hierarchical and the AZP SCHC. So these are the two methods that Luke chose for us to like pay more attention to them. One is spatially constrained, the other that is not spatially constrained. And then once we check all these statistics, like the fragmentation, you can see that the fragmentation that we get from the agglomerative clustering, so the hierarchical clustering, we have the not standardized entropy, the standardized entropy, the Simpson, and the standardized Simpson. So it's basically what we had in GeoDa, right? In the same window there that we plotted. If we did validation on these results, we would get the exact same results that we have here, the exact same numbers. So here we know for the hierarchical clustering, what is the balance that we have, so the fragmentation that we have for each of the clusters. So we know the entropy and the Simpson for each of them, and also the overall fragmentation, right? So you can see that the fragmentation, the entropy is very close to 1. It's not a spatially constrained method, so we do get a more balanced result. And for this, the Simpson method, what we have is also something that is close to 1. So the diversity that we have in number of units between the clusters is very small. If we compare that to our spatially constrained result, since it's spatially constrained, it doesn't make sense to talk about fragmentation for each of the clusters, right? Because they will be all in the same like area, right? They will be contiguous. What does make sense to think about is what is the entropy and the overall entropy and the overall diversity. And what we have here is that now it's worse, right? So the entropy is 0.62 and the Simpson, or the standardized Simpson, is 3.94. Let me just go back a little bit here, because I said it doesn't make sense to talk about the individual cluster fragmentation, but I didn't really explain what it is here. So the idea here is that, let's say, let's choose, for example, cluster 1. So cluster 1 has 26 units in it, right? So 26 municipalities are part of cluster 1 from the hierarchical clustering. Within these 26, we have 14 subclusters. So the idea is that when we look at at cluster 1, at the 26 municipalities, we'll have 14 small groups of them scattered around our map, right? So this is the idea of the whole, how we think about fragmentation when we're looking at this, okay? And then, since we have these 14 subclusters, so these 14 scattered groups of units that belong to cluster 1, we can assess how balanced these subgroups are. And maybe we have, a very large part of cluster 1 in one area, and then very small parts scattered around the map. and things like that. So this is the idea, right? That we're checking what is the balance that we have in these subgroups that are scattered in the map, because it's not a spatially constrained method. For the spatially constrained, we don't have that because they will always be together all the time, right? Because of the constraint. Okay, good. Right, so these are the fragmentation measures. The join count ratio will show, again, will count how many neighbors are part of the same cluster for each of the units that we are evaluating. So again, I just explained these. I won't repeat myself that much, but so we can see here for each individual clusters, what is the ratio that we have. So greater ratio, closer. You would never really have a ratio of 1 here unless you had only one big cluster, right? Everybody was in it because of the border effect. So if you have 2 clusters, you will always have units that will be bordering a different cluster, right? And they may be neighbors if you're using contiguity. But anyway, the closer to 1 means that you have more concise, like more spatial similarity, and units that are neighbors of each other will tend to be in the same cluster. And so we can evaluate this for non-constrained methods and constrained methods. But of course, the overall join count for unconstrained methods will be much smaller than the join count for the constrained method, right? But basically, it's showing us, again, how concise or what is the spatial similarity that you have between all the regions from these solutions. Compactness. So compactness is, again, the whole idea of the circle, right? Thinking about the shape, the polygon that you have, the shape that you have in the region based on this isoperimeter quotient. So it doesn't make sense to think about compactness for non-constrained solutions, right? Non-spatially constrained methods, because again, the units will be scattered all over the map. So if you draw a circle, it will probably be the whole region, right? The whole sample that you have. So it really doesn't make sense. But for the spatially constrained methods, then we get this IPQ, again, as we just saw in GeoDa, we get it for each of our clusters. Diameter, again, same thing. Doesn't make sense to think about it for unconstrained methods because we're checking how many steps we need to take in the spatial weights graph to go from the farthest regions that we have in the cluster. So if it's unconstrained, it doesn't make sense. You get an error message. But if it's constrained, then we get the same result again that we had in GeoDa. So why did I want to show you the notebook, since pretty much it's showing the same things that we had in GeoDa? It's because now what we can do here in Python that is much easier than what we would have to do if we were just using GeoDa, is that since we have everything saved, and in GeoDa we can have everything open, but then we would have to check each of like the between sum of squares to total sum of squares ratio for each of the methods. It will be kind of spread in the different results that we have. Here in Python, it's much easier to collect all these results. So what this cell is doing here is basically collecting all these results from all of the methods that we have, right? So here we create these lists with the methods and the cluster labels, and then we're just naming them for the table that we will show in the end. So we can collect them all in a loop, and then after we collect them all, we can compare them and make sure that we have a more informed solution or informed decision for what method we will choose in the end and what will be the result that we will want in our analysis. So the good thing about PyGeoda and Python is that we're able to check all the results in a much more concise and easier way. The bad thing about Python and the good thing about GeoDa is in GeoDa we could do all the maps side by side very easily and compare, the spatial structure by looking at them, which would be much easier to do in GeoDa than it is in Python. So again, pros and cons. You choose whatever you prefer. You do both, and then make sure that you have a very informed decision. So what we got here is, again, for the hierarchical and the k-means, of course, we have more homogeneity. So WSS will be smaller. The ratio of between to total sum of squares will be greater. and the in the unconstrained solutions, but the spatial similarity will be smaller. So again, do whatever you think it's better. What is important is that at least one way to look at these things, if spatial structure is important for your solution, is to use the unconstrained solutions as benchmarks. So like, you'll never do as good as them in terms of homogeneity, but you can look at the spatially constrained methods and try to see how close you are to the unconstrained solutions in terms of homogeneity, just to see what is the price that you're paying for that spatial constraint. And then, for example, if you look at the AZP with the spatially constrained hierarchical clustering as an initial solution, you'll see that the price that is being paid in this exercise in terms of homogeneity is not that high, right? The homogeneity is decreasing from, let's say, here, 335. The heterogeneity is increasing from 335 to 538. The ratio of between clusters to total heterogeneity is decreasing from 0.7 to 0.51. So maybe it's not too high a price to pay for spatial similarity as well, again, depending on what you need. Then the join count and the fragmentation measures can help you as well. Here, we are not using the standardized measures. The number of clusters is the same, so it doesn't really matter. But if you want to use the standardized, you can just move upwards here in the cell. And like where we do the entropy, you can just do STD entropy. And where we do Simpson, you can do STD Simpson. And then, of course, just add a star here, just to make sure that you know what you're looking at. Oops. I don't know what I did here, but anyway. So yeah, it's still, these numbers are comparable, but if you want to make sure that the closer to one approach is what is guiding you for evaluating this, you need the standardized, because then the entropy will be closer to one will be the more less fragmentation, more entropy. And for the Simpson, you will have the same. So, and another thing that in the notebook in Python we get to do is to actually compute the adjusted rand index. In GeoDa, we could look at the cluster match map, like we could use the link to see how many units that are part of cluster one that are actually part of, the same cluster from another method. We could do that by visualizing our results. Here we can just use the adjusted rand index to sort of count that and count exactly how many of the units that are part of one cluster in one method are also part of this, like the same cluster in a different, from a different method. So these are the external validation measures, because you're not looking at them just from the point of view of that result, right? You're comparing different results. The internal validation measures, like what we get here for the k-means, depends only on the results of the k-means. For the external validation measures, we need two different solutions to compare them. So what we have here is that they're just adjusted rand score when we compare the hierarchical clustering, the agglomerative clustering with the k-means is 0.41. So this is showing that there is some correspondence, right? Correspondence in what we have between the clusters, but it's a low level of correspondence. So it's not very high, right? So the units are not really part of the same clusters when we compare these two solutions. All good? So again, here we're doing only these two, but we can do all of them, all of the methods. We can collect all of the results. So this function is doing exactly that. And then we'll have this symmetric table here. So we can look at it just at the lower triangle or the upper triangle, whatever you prefer. The ones in the diagonal, the main diagonal, of course, we can just ignore them. And then we can see. So for example, if we compare the hierarchical solution with everything else, we'll see that it's not very similar, but the most similar one is k-means. but the result is very different from what we got from all of the spatially constrained solutions, right? So as we would expect, a very different result because now it's spatially constrained, and that constraint is really important to shape the result that we have. So we can do that for any of the methods. And the way I look at this is that we're comparing the solutions, and they are all very sensitive to the choices that we made, right? The parameters that we have chosen when we were running everything. So since it's very sensitive to the parameters that we have chosen, we need to think that maybe if we changed the method and the result that we got was very different from anything else, maybe that is not good, right? Maybe that is not a good solution because it was very sensitive to the method. Whereas if there is any result that we got that was very similar across different methods, then maybe that's a more robust result. So maybe that is something that we should favor in our evaluation, right? So this is the way I think it's a good approach to this index, is that from here you are able to identify the method that have given you a result that is not that odd, that is not that very different from everyone else. So for example, if we check here, again, the AZP with the initial solution, of course, it's very different from the unconstrained solutions, but it's not that different from the spatially constrained, of course, but also from REDCap and also from the standard AZP and even like Skater. It's not very similar, but again, it's not a very low number, like the number is not that low. Whereas for the MaxP solution, for example, it's very different than anything else. So maybe that is not a good thing, right? Does it make sense? So again, you should never base your decision only one thing, because maybe what you got from the MaxP was exactly what you wanted, and it's reflecting what you would expect or what you need for your research. So that would be the solution, different than anything else. But it's one more level of information that you can use. A very similar idea to this ARI, so the adjusted RAND index. And so here Luke is saying that the greatest correspondence is between SCHC and REDCap, which is pretty much almost the very same result, right? So much different methods, and you basically get a result that is almost the same. So this is a very similar approach, the normalized information distance, but instead of counting the number of matches that you have between the clusters, it will look at the entropy that you have. So it will calculate this adjusted mutual info score based on this information, the mutual information score and the entropy. And then what you get when you compare the hierarchical clusters to the k-means is 0.60. So this is the number that we get now. So it's much better than what we have from the adjusted RAND. So this is kind of a high number, showing that these two solutions, they share similar entropy. And when we compare all the solutions again, we can do the same analysis as we did before. And again, the closest correspondence is the same, SCHC and REDCap again. Here it is, 0.897.
Actually, Pedro, that is not surprising because REDCap, if you recall, is kind of a combination of SCHC and Skater.
Yeah.
And it starts bottom up and then it goes top down. So this kind of, to me, confirms that they're essentially doing very similar things.
But what strikes me, Luke, is that it's basically the relationship that you have in REDCap between Skater and SCHC. It's similar to what you have like in MaxP and AZP, right? It's just kind of combining solutions. But the MaxP and AZP, they are not that similar. So this is something that is interesting that, yeah, even though these two pair-wise methods, like when we compare them, the methods are related to each other, but one solution in one pair, the solution is similar, the solutions are similar, and in the other pair, the solutions are not that similar. right? Showing how the MaxP, in this case, resulted in something that is much different than the other methods, right?
Yeah, because in part because of the constraint on the population that's been imposed.
Absolutely, yeah. Oh yeah, the AZP here, we do not constrain it, right? So it's unconstrained in terms of the population. Yeah.
Mhm.
All good? Questions, comments? No? Luke, anything else to add?
No, this is great. Well, I think you mentioned it. The way I have the normalized information distance in the slides is slightly different from what scikit-learn implements. It's essentially the same thing, but they rescale it so that in their index, larger is better. In the one in the slides and in the book, smaller is better.
Yeah. So in the notebook, Luke explains this as well. So you can, there's no way to forget it when you check the full notebook. All right, so time's up. Let me stop this.